Hello my dear students, welcome to the another session of Anand Medical Academy digital classes. Let us start the new topic of the continuation of previous chapter called moving charges and magnetism. The name of the topic of today's session is Ampere's Circuital law and its applications. In electrostatics, you might have learned a law called Gauss law. Actually, the Gauss law is the alternative of your Coulomb's law in electrostatics. In magnetism, in this moving charges and magnetism chapter, there is a Biot-Savart law which we had already learned. And this Biot-Savart law and Ampere's Circuital law both are also similar to the Coulomb's law and Gauss law over there. So what is exactly meant by that? So this Ampere's Circuital law is an alternative form of Biot-Savart law. Like Gauss law is an alternative of Coulomb's law. That's it. So let's start. What is Ampere's Circuital law? And before that, what I have told you just now, I will be writing the same here. You can see here. In electrostatics, Coulomb's law and Gauss law. And this Gauss law is an alternative of Coulomb's law. Similar to that, in our magnetism, here what I am writing, carefully see. So this is Coulomb's law, and here it was a Biot-Savart law, and so many applications also related to the Biot-Savart law we had discussed. And now Ampere's Circuital law. And this Ampere's Circuital law is an application, is an alternative of Biot-Savart law, right? So what is the alternative of Biot-Savart law will be discussed now, okay? By using this Ampere's Circuital law, so there are so many applications I've mentioned here. So let's see. The first application is magnetic field due to a straight wire, long straight current carrying wire. So the magnetic field due to a long straight current carrying wire we had already found by using a Biot-Savart law. Now by using the Ampere's Circuital law also we will be finding the same. So the both answers must match each other. That's called the Ampere's Circuital law is an alternative form of Biot-Savart law which is more easier than the Biot-Savart law. Now the second application was a magnetic field due to a solenoid. In your 9th or 10th standard, you might have learned or heard about a solenoid. So the magnetic field due to the solenoid also we will be discussing here. And the third application is a magnetic field due to a toroid. Due to the toroid also we will be discussing. There is a close relation between solenoid and toroid. That also we will be discussing today. Now, let us understand these applications before moving into the deeper levels of their applications. Initially, we had taken a wire, just a wire, through which a current I passes. This current carrying wire will produce a magnetic field around it, right? Now, magnetic field around the straight current carrying wire, which is finite length or infinite length, all those things we had done by using Biot-Savart law. After that, what we have done, so the same wire we had bent into the form of circle through which the current is flowing. Here also we had identified the magnetic field produced at the center or from the center on its axial line at some points. Magnetic field we had found. Okay. Now, the same wire, if I made like this, of so many closed turns. So this is called the solenoid when the current I is passing through it. It's called the solenoid. Okay. Now, when the same wire is made like this, you can see clearly here. It is called toroid. Magnetic field due to a straight current carrying wire, magnetic field due to a circular current carrying wire, magnetic field due to the solenoid, magnetic field due to the toroid. The same wire we have keep into the different shapes and finding the magnetic field around it and inside it. Okay, so this is what our aim of Ampere circuital law. And what is this Ampere circuital law? And we will be discussing now. Listen to me carefully. The statement of Ampere circuital law is given in this way. The Ampere circuital law, it states that the line integral of magnetic field, around any closed path is equal to mu naught times the current enclosed in that path. See here, this is what Ampere circuital law states that. States that the line integral of magnetic field, what is meant by the line integral of magnetic field? You can see here. So the line integral of magnetic field B bar dot dl bar. Okay. So B bar is the magnetic field along the line integral. So integral, this is a symbol of line integral of a closed path, which is B bar dot dl bar. dl bar is the elementary length, which is equal to mu naught times the current enclosed in that path. So mu naught times the I. I is the current enclosed, that you should understand here. So this is what? So the line integral of magnetic field, and this is I is the current enclosed. I am writing here I is the current enclosed in that path, or current enclosed by that path. So that's important. Current enclosed by that path. Okay. Clear? Now, look at the interesting thing. So there are some sign conventions related to this Ampere circuital law, and especially current enclosed by that path. So the sign conventions we will be discussing now. Sign convention we will be discussing now related to the Ampere circuital law. Let us start. What are the sign conventions involved in Ampere circuital law? So you can see this expression for the Ampere circuital law. Line integral of magnetic field around a closed path which is equal to mu naught times the currents, all the currents are the sum of the currents enclosed by that path. Remember, this I is sum of the current enclosed or the total current enclosed by that path. So let us understand the sign conventions. See, the basic diagram I am just going to draw here. You can see there is a closed path. And before moving to that, listen. In Ampere Circuital law, this is applicable for number one, any closed path, whatever may be the shape and size. Irrespective of the shape and size, Ampere Circuital law is applicable for any closed path or any loop. Okay, and number two is the current. What we are mentioning here, the current which must be a steady current. If it is a variable current, the Ampere Circuital law is not valid. Okay, so this current I must be the steady current. Is it all right? These are the two conditions or two exemptions for Ampere Circuital law. For any closed path it is okay, and for the steady current only you can say these are the limitations, you can say, right? Now, so this is a closed path. Here they had mentioned the direction of the magnetic field in this way. This is what the direction of magnetic field. You can imagine that these are the concentric lines. Okay. Now, here they had mentioned this is the current I1. See, this is not the direction of magnetic field lines. Listen, I had told you clearly during the first or the second lecture in this chapter. Here, the dot symbol is representing the field lines are out of plane. Here, field lines I am not representing with the dotted line. The dot is representing the current here. Current is moving out of the plane. And the magnetic field lines are like this. And there is another current I2 is moving into the plane. And there is another current I3 is moving out of the plane. And outside the loop, there is a current called I4 is moving out of the plane. Okay, so there are three currents enclosed by this loop. The first thing you should understand, see, the question is find closed integral b bar dot dl bar. Okay, so the question is find line integral of b bar dot dl bar around a closed path is how much? Okay, so it is so simple. You will get the answer in terms of your mu naught. Okay, let's start. So closed integral of b bar dot dl bar is equal to, so what is that? So I'm just removing it, is equal to mu naught times the currents enclosed. Okay, currents enclosed. So what are the currents enclosed here? Currents enclosed are I1, I2, I3. I4 is not enclosed by the path. It is outside the closed path. So that's the reason we will not include this here. So now your line integral of magnetic field around a closed path is equal to mu naught into how many currents are involved, how many currents are enclosed by this? I1, I2, I3. You can write I1 plus I2 plus I3. Okay. So if you think this is the answer, it is wrong. Because all the currents are not in the same direction. So that you can add or you can subtract. But this is not in the same direction. So what you have to do here, I told you already, the aim of this part of the lecture is sign convention. So let's understand the sign convention now here. You know the concept of right hand thumb rule or reverse of the right hand thumb rule. So let me write here, according to the reverse of right hand thumb rule. According to the reverse of right hand thumb rule. What is the reverse of the right hand thumb rule? You can see here. Imagine your curl of the fingers are giving you the magnetic field direction. So if the curl of fingers are giving you the magnetic field direction, look at here. if the curl of the fingers giving you the magnetic direction and a thumb will gives you the direction of current. Okay, so thumb gives you the direction of current. I told you right hand thumb rule, and I had also mentioned that the reverse of the right hand thumb rule is also true, which is thumb is giving you so the direction of current. If you place your curl of the fingers in the direction of magnetic field. Okay, so when this condition is satisfied, so then you can write so that current direction is positive. When this condition is not satisfied, you can tell that the current direction is negative. That's so simple. So let us check whether the direction of currents is satisfied or not according to this given diagram. And let's keep the curl of the fingers in the magnetic field direction. You can see right hand, curl of the fingers in the direction of magnetic field. You can see curl of the fingers in the direction of magnetic field, and the currents are moving out of the plane. And what all the currents are moving out of the plane? I1 and I3 are moving out of the plane, and they must be taken as positive. Okay, so now which is mu naught into, what are the positive currents here? I1 plus I3, I1 plus I3, and this is the current is into the plane. You can carefully see here. So if I place the curl of the fingers in this direction, so outwards must be the current direction. So but this is inwards, so that indicates I2 is negative. So this is the concept. It's so simple, right? So mu naught into I1 minus I2 plus I3. So that the line integral of magnetic field around a closed path. So that's the concept. So many numericals you can make by using this, but this is a basic idea I have given about the Ampere circuital law. Okay, now we had already discussed about applications of Ampere circuital law. So the first application was magnetic field due to B bar due to a long straight current carrying wire. So about this we will be discussing now. Before that, you may tell me that, or you may ask me that, sir, already we had discussed this B bar due to a long straight current carrying wire by using Biot-Savart law. What was that expression? What was that expression? Magnetic field due to this long straight current carrying wire. So this is a long straight current carrying wire. Long means infinite. Okay. So at a distance r at point P, you know the magnetic field at this point is into the plane. Again and again I will not show you why we wrote the direction of the magnetic field at this point is into the plane. Okay. Now at this point you can say phi 2 is 90 degrees, and at the same time phi 1 is also 90 degrees. And what is the magnetic field at this point? B is equal to mu naught I by 4 pi r into sine 90 plus sine 90. So here it is 2 and 2 2's are. So magnetic field due to a straight current carrying wire, which is long straight current carrying wire, is mu naught I by 2 pi r. The same thing we will be deriving by using Ampere circuital law also. Just keep this equation in your mind, mu naught I by 2 pi r. Let's see the topic called magnetic field due to a long straight current carrying wire by using Ampere circuital law. See, to apply an Ampere circuital law, we need a current which must be enclosed by a particular loop. Okay, that loop will be having a magnetic field. Let's check here. So this is a straight current carrying wire, which is I, Around this, magnetic field lines will be concentric circles. So many times we had discussed, and the concentric lines direction, those are the magnetic lines of force, or magnetic field lines direction is, for example, this is the current carrying wire. Current is moving in this direction, upwards. When I look from here, you know, by using right hand thumb rule, this is the thumb pointing in the direction of current, and see the curl of the fingers are representing the magnetic field lines. And when I see from the top, the curl of the fingers are like this. That is called anti-clockwise. Yes or no? This is the current carrying wire. In this direction is current is passing through, and you can see the curl of the fingers. When we see from top of this wire, the curl of the fingers are in this direction, so that's called anti-clockwise direction. Okay, so now the representation of the anti-clockwise direction is like this. Clear? Sure? Now, you know, at any point if you want to find the magnetic field line's direction, so you should draw the tangent line that is called a B bar direction, and that is a small element, let's see, a DL bar direction also. In this case, what is the angle between B bar and DL bar? 0 degrees. So I am writing here, so the angle theta between B bar and a DL bar is 0 degrees here. Keep it aside. Why we are finding the angle between them? I'll tell you later. Listen to me. Right? Now, we know that line integral of the magnetic field around a closed path is equal to mu naught times the current enclosed. Here, the current enclosed is positive because only one current is there. That is also according to the magnetic field lines. You can check here. So according to the magnetic field lines, the current direction is satisfied. So now B bar dot DL bar is equal to mu naught into I. So here, closed integral B dl cos theta. Will you agree with this? Because it is a dot product. Dot product, there will be a cos theta will come here. So B bar dot DL bar, which is B into DL into cos theta, which is equal to mu naught into I here. So B DL cos theta, what is our cos theta? 0. So cos 0 is how much? 1. So what I can write? Closed integral B DL is equal to mu naught into I. Okay, so B is constant. So constant magnetic field, because of the constant current, as the current is constant and the magnetic field produced around this also will be constant. So as B is constant, I am just taking the other side, taking outside. So B into closed integral of DL, which is equal to mu naught into I. Here comes an important point. So B into integral DL. So this is the DL, right? One small element, small length element. If you take this small element DL, if you take here also small element DL, small element DL, small element DL, for the complete loop, if the sum of these all DLs will be how much? The sum of all DLs for the complete loop, can I say it is 2 pi r? Yes or no? So definitely it says because it is a circumference, right? So if you consider the radius of the concentric circle is r, and the length of this complete concentric circle will be 2 pi r. So 2 pi r is equal to mu naught into I. So the magnetic field at any point here or here, any point at a distance r on the concentric circle, so that is equal to mu naught I by 2 pi r. So this is the magnetic field due to a long straight current carrying wire by using Ampere circuital law, and by using Biot-Savart law also we have got the same. I hope you could recollect the expression just now we had discussed. Right? So B is equal to mu naught I by 2 pi r. And so many numericals also we have done on this. So mu naught value is 4 pi into 10 raised to minus 7 Tesla meter per ampere. So what is this mu naught? So mu naught is permeability in free space. Permeability of free space, that's a mu naught. Okay. Right? Now, but before moving to the next session, I just wanted to give you a small introduction. So simple. This is a very thin, straight, long current carrying wire. If it is not thin, right? This is what? This is called a solid, long, straight cylinder through which the current flows, right? This is what the axis of the cylinder, and you can imagine that the current I is flowing through the solid cylinder. Solid cylinder means, so through the each part there will be current flowing, not only on the surface. For example, if I say that hollow cylinder, so here how the current flows, you can see this is what the hollow cylinder. Here the current is flowing only on the surface of the cylinder because there is no matter inside. It is hollow cylinder. Current is flowing here and here. Okay, clear? Now, here you can see the radius of this cylinder R. So here also the radius of that cylinder is R. Here there is no radius you can mention because it is a very thin, straight, long current carrying wire, but they are thick, straight, cylindrical shaped current carrying wires. So in these cases also, how to find the magnetic field at some point R from the axis of the cylinder. Here also, from here at some point R, at some point P at a distance R from the axis of the cylinder, how to find the magnetic field in both the cases, let us understand. So the magnetic field in these cases at point P. At point P, we have to find out. Let's continue the session. Magnetic field due to a solid cylindrical wire of radius capital R. There is a magnetic field produced by the solid cylindrical wire. That means through which a current I is flowing. So I am writing here, I is the current flowing through that. I is the current flowing through the wire. Through the complete solid cylindrical wire, the current flowing through this is I. Okay, now let's start. So this is a solid cylindrical wire. So I'm just taking a rough diagram here. So this is the cylindrical wire I have taken, having the area of cross section is A. Okay, so this is the area is pi r square because area of this surface, area of this cross section I am talking about. So that is, so this is capital R is the radius of this cylindrical wire, and this is called the axis of the cylinder, axis of the cylinder, central axis. Now, you know, magnetic field through which the current I is flowing, you can see here. So through the complete wire the current I is flowing through the complete wire because it is a solid. So the complete wire current I is flowing. Now because of this current, I am just going to find the magnetic field at 3 different points due to this wire. The first point I am taking here somewhere here, that is called outside the cylindrical wire. So that is the point from the axis of the cylinder. Imagine this point is lying at a distance R. The first point, let me say the first point. At first point, the distance between the axis of the cylinder and the point is greater than the radius of the cylinder, yes or no? So what I am doing the first case, so the distance what I have considered is greater than radius of the cylinder. And the second point I am considering exactly, this is the infinite, this you should understand. So this is the infinite long solid cylindrical wire. So I am writing here, it's a long one. Now the second point I am taking here from the axis to the point P, so that is at a distance r. So that is the second point. So second case, so when small r is equal to capital R, so that is my second point where we are going to find the magnetic field. Okay. And the third one is inside the cylinder. Inside the cylinder. Imagine, so the point is like located here. So this is the point number 3 and this is point P here. So from the axis of the cylinder, it is at a distance r. So now the important thing, now your small r is lesser than the capital R. These are the 3 cases we are going to check now, right? So what is that? The first point is outside the wire. So I am writing here. So this is outside the wire. So it is on the surface of the wire, and the last one is inside the wire. So if you really understand the magnetic field due to a solid cylindrical wire of radius r condition, it will be very easy for you to find the magnetic field due to a hollow cylindrical wire having radius capital R through which the current I flows. Right? So let's understand this first. So what's the first case? First case is when small r is greater than capital R. By using Ampere circuital law only we are going to do that. So when small r is greater than capital R, so let me see, this is the point P. So if you consider this is a current carrying wire, you can see this is what? The magnetic field lines. Okay, this is the magnetic field lines. You know, closed integral B bar dot dl bar is equal to mu naught into I. In this is called the Amperian loop. Okay, so in Ampere circuital law we will be always finding a loop of any shape or size. That loop is called Amperian loop. What is this loop? So I am writing here. So Amperian loop. Okay, so this is your Amperian loop. So in that loop, only current passing is I, right, through the cylindrical wire, and mu naught is constant here. Here you should understand. So there is a constant magnetic field of this concentric circle, so that is B. If you take B outside as it is constant, closed integral of dl, which is equal to mu naught into I. So here B is into closed integral dl of this concentric circle, integral dl is 2 pi r. So this we had already discussed, but again we are going to do that. Again we are just deriving it. So magnetic field at first point is equal to mu naught I by 2 pi r. It is similar to the condition of magnetic field due to a straight current carrying wire. Okay, so that is what mu naught I by 2 pi r. And the interesting part here you should understand, so the B is inversely proportional to R. When the point taken or point of consideration is outside the cylindrical wire, magnetic field due to that wire is inversely proportional to R. And the second case is small r is equal to capital R. In this case, directly you can substitute small r in the place of small r, capital R here. So B2 is equal to mu naught I by 2 pi into capital R. Okay, so this is what the second expression. And the third expression is very important for this. Any students can do this first two cases. The third case is very important because it is inside and it is a solid cylindrical wire. Okay, and let's see the third case, especially I am writing here, the third case is when your small r taken is lesser than capital R. Where is the small r position? So this is the third case. Okay, we need to find Amperian loop. Look at here. So this is the Amperian loop here. So small loop you can see, that is called Amperian loop. And in this Amperian loop, the current passing through is also very important for us because we know closed integral B bar dot dl bar is equal to mu naught into I. Here I is not the total current passing through this loop. Total current passing through this area pi r square is I. So look at here. So total current passing, total current through an area called pi r square is I. Understand? But our Amperian loop in this case is only this much. So that means only some amount of current will be passing through this loop. Okay. So if it is a total current passing through the cylinder, only some amount of current passing through this loop. So what is that some amount of current? I'm just naming it as I dash. So that's the reason. So closed integral b bar dot dl bar is equal to mu naught into I dash. Okay. So what is that I dash? That's important here. So now current through pi into small r square is I dash. So where is pi into small r square? So this is small r, right? So area of that loop. Okay. So this is area of the complete area, this loop. Okay, only this loop. So if you cross multiply here, for pi r square value it is I. For pi small r square it is I dash. So now you can simply write I dash is equal to how much? I dash is equal to I into pi small r square by pi capital R square, pi cancel, and I small r square by capital R square. That's I dash value. Okay. Now you know this I dash value. You can substitute in Ampere's circuital law. So what I can write, b into closed integral dl bar is equal to mu naught into I dash. What is I dash? Small I r square by capital R square. Okay. So here, so what you can write? So b into it's 2 pi into r. What is dl bar? So this is integral dl bar is, so this is 2 pi r. Small r is here. So now which is equal to mu naught into I into small r square by capital R square. Small r cancel here. Now, so b is equal to mu naught I into small r divided by 2 pi capital R square. And if you understand this concept carefully here, in this case b is inversely proportional to r. Here b is inversely proportional to r only, but here r is the radius of that particular cylindrical wire, and this is the most important here. What are the constants? You identify carefully. Mu naught is constant, I is constant, but small r is not the constant, because inside the cylindrical wire our assumption in this case is r is this much. That r may be this value, r may be here, r may be here, r may be here. Understand? Inside at any point, that means small r is variable and capital R is constant. Radius of the cylindrical wire 2 pi is also constant. So that's the reason b is directly proportional to r. I can write. Got the point? Clear? Sure? So b is directly proportional to r and b is inversely proportional to r. So what you will be understanding? So from the axis of the cylinder, b is directly proportional to r. So the magnetic field is increasing from the axis of the cylinder. The magnetic field is increasing with the distance taken by the body. So from the axis it is increasing and reaches the maximum value on the surface. Okay. And from the surface, when the point is taken away, the magnetic field is decreasing. You can see this equation. Outside the cylindrical wire, field is decreases. Inside the cylindrical wire, from the axis, increasing. Okay. And look at this expression, inversely proportional to r, and it is directly proportional to r. So let me draw a simple graph also between b and r. So this is b and this is r. So this is the origin. Let's see. From the origin is the axis of the cylinder. So from here, what happened? B and R, relation between them is directly proportional. So directly proportional graph will be like this. So here B is directly proportional to R till when R is equal to capital R. So the maximum value it is obtained, understand? So the maximum value the B is obtained when small r is equal to capital R. So that is what from the axis to the surface. And from the surface, what happened? So when the point is taken far away, the B value decreases. So decreases in this way. So this is B is inversely proportional to R. Okay. So this is the important graph for the solid cylindrical wire. If it is hollow cylindrical wire, what is the concept? If it is hollow cylindrical wire, let us talk about the first case. First case is same. If whether it may be hollow or solid, first case the point P is located here. So Amperian loop, if you draw, the current passing through this I only in the loop, and you get the same equation, B is inversely proportional to R. On the surface, B is equal to mu naught I by 2 pi R. These two cases are same. Now, third case, at any point inside you take it, in that there is no current passing through it, because in the solid cylindrical case, so current is passing through each and every part of the cylinder, whereas in case of hollow cylindrical part, there is no matter of the medium inside the hollow cylinder to pass through, the current to pass through. Only the current will be passing through the surface of the cylinder because it is hollow, right? So here, if you take the loop, through this loop, no current will be passing through that. When no current passing through that, according to Ampere's Circuital law, so that will be zero. The magnetic field due to that will be zero. So here, this is solid. If B is equal to 0 in case of hollow cylinder. In case of hollow cylinder, it is 0. So that means from the axis of the cylinder, inside the magnetic field is 0 and on the surface it is maximum, and from here it is decreases. So B is equal to 0. So B is equal to mu naught I by 2 pi capital R. So B is inversely proportional to R. So that is a hollow cylinder. Okay, and in hollow cylinder case, how the graph can be drawn, I'll just show you here. So this is B and this is R. You check hollow cylinder case graph. So this is origin, and origin, to imagine this is what surface of the cylindrical wire. Origin to surface, there is no graph because magnetic field is 0. From here the graph starts. From here the maximum value you get here. So from here graph starts and B is inversely proportional to R. Okay, so B is equal to 0 from origin to the surface. So B is equal to 0. Okay, clear? So this is what for hollow cylinder. So sorry, this is for hollow cylinder, this is for solid cylinder. Okay, so I'm writing here. So this is for hollow cylinder and this is for solid cylinder condition. So important graphs in NCERT or in some books, whatever you are referring for, this may not be there, but this is very important topic, especially for your NEET point of view.